Hello everyone, it's Francesco Canora here, and I'm presenting you a new video with Mule4 about stateful processing using NoSQL DB Redis on a use case which is credit card fraud management. We know that Mule has an object store which can store key value pairs. It's useful in many situations as a cache and other situation, but in this case, for this, we need to use a very fast and scalable and capable key value store. And Redis is a very good candidate. You can check it out at redis.io. Has many capabilities, an open source key value store that is very fast and is a memory backed on disk, very scalable. So let's. I'll leave you. Of course, I cannot. I don't have the time to talk at length about Redis, but we'll see how Redis can be used with Mule4 through the Mule4 connector for Redis. So that's taken from the Redis website, redis.io. You can see there are many commands in different categories. So these, the basic category is string, the easiest is string, so which allows you to store a string value, possibly a very long string, against a string key, which is also string. And then there are more advanced functionality like lists, sets, sorted sets, stacks, hashes, etc. We can see, for example, in this slide that if you use a string commands, you associate a key like k1 or k2, which are strings, with a value, which are also strings, v1, v2. You can set a key value pair, you can get it, you can delete, you can do other things. It's important to note these keys can be set with an expiration time, with time to live, so they can be purged automatically after a certain time, and this time can be set by in absolute terms or by a date, and can be forever. So if we limit ourselves to string key value pairs, then it's similar to what we have in the object store, but there's much more. We can have a hash where a key, there's always a key we need to refer to. This key tree can contain a hash which has subkeys, which are called fields, so F1, F2, etc., Fn, and each field in a hash can point to a value. So we have a two-level structure, which is more powerful and flexible. Then we have a structure like a list, which allows inserting and removing elements in at each end of the list. So it can be a list, a LIFO, FIFO, it can be a stack. You can access by index in the middle, etc. Then also we have sets, so we can have a key associated with a set of elements where Redis recognizes whether an element is already in the set or not. It can add, remove, check for membership, and do a set intersection, a union, and difference. So what you can see on the next to the arrows are the names of the Redis commands that you can find on the documentation. In this use case, we'll use something more sophisticated than a normal set. We can use a sorted set where it's like a set, but each value is associated with a numeric score, which is an integer, can be positive or negative, and Redis keeps the value sorted at all times according to the score. So that is useful because then it allows us to select based on the store, to have a ranking of the values, and also select based on the range of scores. And we'll see how we can use it in our case. So there's even more functionality like streams and etc. That is it's we're not going to talk about that here. So let's talk first. Introduce the Mule4 Redis Connector. You can see the screenshot from Anypoint Exchange. It's a select connector, so it's supported by MuleSoft. What you can see on the right side are the connector operation implemented by the Redis commands implemented by operations of this connector. There are quite a few, but there are not nearly as many as there are Redis commands, as you can see from the Redis side. So functionality of Redis is much wider than what is covered by this connector, but still it's very useful. If you need more, you need a full client library for Redis, such as lattice.io. You can check it out. It implements everything you can wish for. So in this case, you could, of course, include this Java library as a dependency on your new project and use a Java connector to invoke methods. But then this is not needed here. In this case, we'll simply use the commands. Exactly the commands we're going to use relate to the sorted sets. So you have and the expiration of the key. You can see from the top of the commands there is a command called expire at and expire. You can set the expiration of the key, after which you get the automated purge, and then you can get if you're more or less in the middle, get range by index and get range by score, and we'll use get range by score. So we're going to insert entries into this sorted set, already sorted set. Our Mule application will insert these entries, and then we're going to check against this sorted set, and as I will describe. Okay. So their use case is kind of simple. Of course, it's a use case of credit card fraud detection. But of course, sophisticated credit card fraud will be done with stream analytics or machine learning. This is just a simple example. You know that one rule that can be applied to credit card transactions is that if there are two transactions, they're close enough in time, and they are done from very far places, then it might be a fraud. For example, if there is a you can see the JSON on the top, JSON document, which represents a credit card transaction. This is a transaction done on the 23rd of May, and it's done in Paris. It could be a point of sale of a shop, or it could be an online purchase where the IP of the internet provider is the reference for the sale location. So the sale location can be a physical point of sale or the internet provider location. So but anyway, it identifies more or less where the purchase was made, the transaction was made. And in the JSON document below, you can see another credit card transaction for the same credit card, and it's in the same day. So again, the 23rd of May, but it's in Denver in the U.S. So because it's unlikely that somebody traveled in one day from Paris to Denver, it's not impossible, but there is a chance. Because these transaction timestamps are less than 1 day apart, and the point of sale location are more than 1,000 kilometers apart, very far apart, then there's a chance of a fraud. The fraud took place. So an alert can be generated to the cardholder, to the bank, and therefore to the cardholder. So this is the case. So we're going to use as input, this simple JSON document will be produced. So we assume we feed into our Mule application this kind of document. What we want to do is that whenever we receive one JSON document for a new transaction, we insert into Redis as a sorted set whose key corresponds to the credit card number with a prefix card dash. So the key, there will be one sorted set per credit card, and into that sorted set we put all the transactions for that credit card within a certain time, of course, because if there are no transactions for some time, we want to expire the sorted set and purge it. So this is not meant as a persistent store of credit card transaction, but it's just a temporary store to be able to perform this check, this fraud check. So we enrich the JSON document with the geo coordinates of the point of sale location. So from the location we call an API, public API to determine the latitude and longitude of this location, and then we compute a score, which is just a translation of the transaction timestamp into seconds from the epoch, the Unix epoch. So just an integer number that represents the point in time where the transaction happened. So after storing this transaction with time and geographical coordinates, we check whether there, for the same credit card, there are transactions which are close in time, plus and minus 1 day, and far apart in distance based on the geographical coordinates. So this is the what the check we're going to do for every transaction. And then we set a time to live of the sorted set of 5 days. So after 5 days there's no transaction for a given card, the sorted set of the card gets purged. So this kind of storage, so storing this kind of information with a timestamp and checking and this kind of query, of course, could be done on a relational database, on its normal SQL database, but the point of using Redis is very, very fast. It's in memory data store, so it will be much faster than if it properly installed, much faster than a SQL database for a large volume of transactions. So then we'll switch and see to Anypoint Studio and see how this logic works. This is the Mule app. It's called Fraud Check. The top level flow is on the top. We use HTTP listener, but of course it could be a JMS queue or something else to trigger this flow. We assume that we received this JSON document that we saw before, the kind of JSON document for the transaction through HTTP request. And what we do, there are two steps. We insert this into the sorted set for the card, and if it's a duplicate, it will not be inserted duplicate because it's a set. And second step is the check against the timestamp and the distance, and check for the current transaction whether there are, let's say, flag transactions which are close enough in time and far enough in distance. So the first step, insert transaction into store. Okay, this I will not go into all details because you will find this project on GitHub, so you can check for yourself all the details. Of course, I've installed the Redis Connector from Exchange with the list of operations that you saw before in the slides. And I've created a global element for the Redis connection. with properties from a properties file. The Redis DB that I have is a local and runs on a standard port 6379, as you can see. I will use this Redis client, Redis-CLI, which comes with a Redis installation to check what's in the database. So let's go back to the flow. In the private flow that insert transaction to store, I first set some variables. Set multiple variables to a transform data-weave transformer. So first is the expiration time, so the current timestamp plus a property which keeps a second. Let's say you want to expire the sorted set in 5 days, and I have the number in this property, the number of seconds corresponding to 5 days. The transaction timestamp, okay, just very simple, taken from the payload. And the store key again is just the card number from the payload with a prefix card dash. So all very simple. The next step is to get the sale geographical coordinates. So we're gonna call this other flow. This flow gets sale location coordinates, has calls a public API, which is just for testing only because a free API, which cannot be used for heavy volumes. Apologies for these delays. So this it's the OpenStreetMap API, and this gives given a query parameter. Given the query parameter of the sale location, gives the document with the geographical coordinates. Then we'll map these coordinates because this only because the API returns more information. You can look at that. After this, we're going to add this information to the payload. To add, I use a new Mule4.3 new operator update in DataWeave 2.0, but it's only supported from Mule4.3, which is a handy way to add something to a document, to an object in this case. So after we add this coordinate, use a Groovy script to compute the score. This is just a translation of the timestamp of the transaction timestamp, which I've stored in a variable before. It's a string with and it's translated into milliseconds, and then I divide by 1000, so it's seconds, and for practical purposes it has to be negative because of the way I set up the scoring. So this will be a value of the score. Then we insert it into the store. That's pretty simple. We use the store key. The store key, as we said, is a card, a number with a prefix. And then because we have to insert a string, we need to insert this JSON, what we mapped before, so the enriched transaction plus the enriched with the geo coordinates as a raw string. So that's the way to do it in DataWeave. And we add the score, which was computed by the Groovy script. So, and then we say that this key, so the associated sorted set, is going to expire in 5 days. So a store key expiration we saw before, it's set with the current timestamp plus 5 days. So whenever there's a new transaction for that card, for a given card, then we extend this expiration by 5 days. So if for 5 days there is no transaction for that card, Redis will purge the sorted set, so it will be deleted automatically, and then we start from scratch. So we don't keep the complete history of transaction per the card, but we only keep the data if there's something happens every 5 days as a minimum. So after having inserted, we save the original payload, and then what we need to do is to get the current transaction coordinates, and we get the transaction in the set which is corresponds to the score within the tolerance of let's say 1 day, plus and minus 1 day. So the timestamp of the score minus plus and minus the property that gives the seconds corresponding to 1 day. So we're gonna get the subset from the sorted set, which is within 1 day plus and minus 1 day of the current timestamp. So that's the way we do it, and this will return an array. We iterate on the array with this for each scope, and then for each element of the array. So we know that if for this array the transactions contained in it are within plus and minus 1 day with respect to the current transaction that we're processing right now. And then we check the distances. Here we call this flow to compute the distance in kilometers. This is done again with a Groovy script. It's use simple calculation, which is a spherical law of cosines. This is not the most exact distance, but it's good enough. And so we assign a distance between the current transaction and the transaction that are in this subset of a transaction for the same card between yesterday and tomorrow. We go plus and minus 1 day because this transaction could be reported out of order. We could have a transaction of yesterday or some days before reported only today, and so we cannot just assume that all points of sale will report in the same order. So after we get the distance, then the next step is to check so first we get the distance, and then the next step is to check if the distance is less than the tolerance. So the tolerance is 1000 kilometers. So we have in this choice router, if the distance in kilometers, which is a variable I set before here, this compute distance has saved the result in a variable called the distance in kilometer. If there's more than 1000 kilometers, which is kept in this property, then we're going to collect these transactions, which will be flagged. And then here in the last step, which is format response, the flag transaction will be added. So the response will be the current transaction plus the flag transaction, transactions which are in doubt because they're too close together in time and too far apart in distance. The flag transactions are accumulated in this variable, which is set outside the choice scope, and then in the choice scope this in this choice scope, what it does here is to add, if it's to be flagged, is to add this transaction. So again, I leave it to you to clone this project from GitHub and to see all the details. Now I've already started it. Let's see how it works. I prepare in Postman 5 transactions where you can see the location, and in this collection you see the location and the day. So we assume the customer is for a lady from Paris, and there is a purchase in Paris on the 23rd of May. Then there's also purchase in Lille, in the north of France, 24th of May, a purchase in Lyon, 22nd. So Lille and Lyon are within 1,000 kilometers of Paris. Then suppose there's also a transaction in Milan, which is also within 1,000 kilometers of Paris, but also you can see is an older transaction that came in and the 19th of May, and then it's outside. It would not be included in a scope of minus or plus 1 day. So let's see. So let's first submit this transaction in Paris, and you can see we get a response with the part of just the key sum of the data of this transaction. The flag transaction is an empty array. If we look at the what keys this Redis database contains, you can see it contains a single key for this card. This is a key of the sorted set. Let's see what this sorted set contains. We're gonna just select 10 elements from 0 to 10. They're sorted, and you see there's only one element for this transaction, and you can see the sale coordinates, geo coordinates, and they were computed by the API, retrieved by the API, and added by enrichment before this was stored in Redis. So let's do another. Let's do Lille. You can see again there's no flag transaction. If we repeat the query in Redis, you can see the second one. But then suppose we get something from Chicago, and here we see a difference because there is a transaction coming from Chicago from the 23rd of May, but then at the same time there was also transaction in Paris, same day, which is 6,650 kilometers from Chicago. So there's a flag transaction that could be flagged. So if we say Denver, we have again flagged distances. So the current transaction is Denver. Denver is more than 1,000 kilometers away from Chicago. Is even further from Paris and Lille. So you can see if we say Milan, this is an older transaction on the 19th, and there's nothing close in time, which is within a day of this transaction. So in this case, we don't even check the distance, because we check each transaction when it comes against the transaction which are plus and minus 1 day in time, and only for this we check the distance. So we can see now that the Redis database contains all this data, and this is kept sorted, as we said, and then searched very efficiently. So this takes very little time. So I encourage you to clone this and to test it for yourself. There are a couple of transactions in the test resources that you can check. So I'll leave you to that, and we'll talk to you for the next video. Thank you.